All right. Okay. 9, 9, 8. So excluding me, right? 8. Okay. So it seems like 13 students registered for this class, but we have 8. So 5 missing. Okay, let's wait. Okay. Okay, let's get started. I think last time I did a good job and scare away, some of you. And so I expected a less student, but now we have 2 more. Some out, some in. So we have some new faces here. Okay, Dongwon, the webcam is working, right? Microphone is not working though, right? Okay. 경철 is not here, right? 승태? 승태? 준영? 김준영? Okay. 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 One announcement. I forgot to mention this last time. There is a first assignment out, okay, on class page. The first assignment is always super easy, right? So the first one is installing the CAD tool we are going to use throughout this semester. So you click on this. So install Vivado 20.1 with Vitis on your PC, because we are going to use that CAD tool, this CAD tool throughout this semester. So to install that tool, you go to Vivado, right? Vivado Xilinx, okay, download. Then here, download page, right? And there are several versions here. That is the latest one, 21.1, latest one, but we are not going to use this one. There are, so frequent update. So sometimes it is hard to keep up with, new updates. So here, this one, 20.1, okay, 2020.1. So scroll it down, then unified installer. So 10.3, I think this one. So check this out, unified full production. So which one? Windows, I think, depending on your machine, Windows or the Linux, right? So the image is huge. If you download the whole image, I think that is more than, 10 gigabyte. I think 20 more than 20 gigabyte. So make sure you have enough hard disk space. And at the end of the installation, you need a license. License is very expensive. One copy, it costs more than $5,000. 500만 원, more than 600만 원, $1,000. But I have 50 licenses donated from Xilinx. So I think Himin, you are managing Xilinx license. 구윤, do you manage, or who is managing? 희민, 구윤?
일단 상호 형이 가지고 계십니다.
Okay, Sang-woo is not taking this class, right? So who? 구윤, can you? 희민, can you?
네, 제가 그 메일 주시면은
Yes. So
나눠.
yeah, you guys can send the email to Himin. Okay, Himin. Okay, send email to Himin. Then Himin will generate the license and email that license to you. But when you send the email to Himin, you have to provide what information? I think MAC address. Okay, so let me go to the license page. Okay, Xilinx license, right? License manager, like this. Solution. Where is that? License. Okay. Okay. What is that? Hope this is correct. Oh no, not correct. Okay, I don't know. I forgot. Oh, let me try one more. Oh, okay, working. So here, Himin is going to follow these steps to generate a license for you. But what you have to provide to Himin is manage license. Create new license. I have design suite. February, this one, right? This one. Okay, 25 licenses. Okay, generate node locked. Okay, select node locked license. Host. Yeah, host machine. Himin needs your computer's information, like host name, right? Check this out. Host name and Windows 64-bit or Linux. Okay, host type. So probably you have to provide this MAC address, Ethernet MAC. Okay, MAC address, because Himin need to enter your MAC address here. Okay, I think that's it. Host name. Okay, host name and MAC address. Okay, host name, MAC address. Then Himin can generate the license and email to you. Any question about this? Okay, that is the one that is about first assignment. Okay, let's continue the lecture. We are still in the first week, so today's lecture will be also very introductory. So this slide, this PowerPoint, I want to compare these two, embedded systems versus general purpose computer system. How embedded systems are different from general purpose computer system. Last time I briefly explained to you what is embedded system, right? Embedded system is what? Specially built computer system, special purpose computer system. Okay, computer system inside a car, computer system inside TV, computer inside microwave, refrigerator, you name it, everything except your desktop notebook computer. Right, that is embedded system. Okay, but we want to go a little bit further to technically explain the difference between these two. What differentiate embedded system from general purpose computer system? A little bit more technical discussion. Okay, first, the big picture. Okay, this one, Jinuk, can you please?
Embedded systems are virtually everywhere in your life. Embedded systems cover a wide range of electronic gadgets such as iPhone, Android phone, GPS, refrigerator, washer, TV, and so on.
Okay, essentially everything except desktop or notebook computer, right? Computer inside refrigerator, washer, TV. Okay, again, there is a debate, right? About this smartphone. Is it embedded system or general purpose? Okay. Anyway, let's categorize smartphone as one kind of embedded system right here, and GPS, gaming console, and so on. Okay, those are examples of embedded systems. Okay, Himin, can you please?
Embedded system is a special purpose computer system designed to perform one or a few dedicated functions.
Yes, special purpose, right? So again, the computer inside TV is responding to your remote controller, right? Also, computer inside TV is displaying what? A program guide. Okay. So by looking at program guide, you can reserve the program you want to watch later on, right? Just reserve it, right? And time's up, then that that program will be played. And GPS, computer inside GPS navigator, that is designed to show you, guide you the shortest path. Okay, so you set destination before drive a car, then the computer is computing the shortest distance to the destination. So you can just follow the path, right? And computer is built only that purpose, no more than that, right? So special purpose. Okay, so let's categorize a smartphone as one kind of embedded system. Then I want to show you how competitive embedded system market is. Okay, look at this. Look at this iPhone generation. Do you have more? Okay, that's it. So actually, look at this number. 2007, 2008, until 2014. Every year, actually, I updated this PowerPoint. But after doing that for how many years? 7, 8 years, I lost my appetite. Okay, I'm sick and tired of updating this, new product slide. But the important thing is look at this. The timeline. June 2007, first iPhone. June 2008, June, every year, right? Every June. Then there's a hiccup, October. Then September. Every September you see a new iPhone, right? What do you think? So there's a hiccup between 2010, 2011. What do you think happened during this time? Why hiccup there? Mingyu, what happened during the time? Famous person passed away, right?
Jobs
Yes,
was
yes,
dead.
yes.
Yeah.
Steve Jobs passed away, right? So I think sometime in September, right? 2011. So there is a hiccup. So 1 year, right? 1 year, but here 1 year and 4 months, something like that, right? 1 year and 4 months. Now, but September. So Intel, not Intel, Apple managed to push their employees, right, to be back on track, right? September to October to September, 11 months, right? So how about Samsung Galaxy? Look at this. So I tracked new Galaxy until 2015, and no more, right? No more update. Okay. So June, look at this. June, May, 11 months, right? May and April, 11 months, another, right? April to 1 year, and March. Mingyu, what happened? Mingyu is from Samsung. Samsung, and Samsung is pushing their employees very hard, right, to reduce this, rollout time, right? 1 year, sometimes 11 months. Now, sometime in February, right? Okay, don't work too hard, Mingyu. Okay, at Samsung.
I think Samsung plan to publish the Galaxy Note in that year.
Oh,
I
really?
guess this just guess.
Yeah, okay. Okay. So, then not only Apple, smartphone and Samsung smartphone, there are a lot of smartphones, right, in the world. So look at those, smartphones from Google. I should update this PowerPoint. smartphones are, smartphones are, designed, not only Samsung and Apple, right? And Google, I think HTC is almost dead. I haven't seen HTC smartphone. And, there are several Chinese companies like Xiaomi, right? And Vivo, Oppo, right? And Nokia is also, right? Nokia is also producing a smartphone. What else? Xiaomi, Huawei, right? Vivo, Oppo, LG's phone is dead now, right? So anyway, there are a lot of smartphones rolling out every year, right? Every year, so many smartphones rolled out every year. That means the smartphone market is super competitive, right? To consumer like us, we have a limited budget, right? We don't want to spend too much money on smartphone. If the functions of the smartphones are similar, we want to purchase cheap, cost-effective smartphone, right? So when you design smartphone, you have to keep that in mind. Customers have a limited budget, right? And you want to make sure you are providing good performance, and also power consumption should be very low. Okay, and performance, power, cost, right? The price should not be that expensive, right? Those things. Okay, so the common characteristics of embedded system. So there are 4 characteristics. Sang-won, can you please? I cannot hear you. So.
들리죠?
Mhm.
Even though embedded systems cover a wide range of special purpose systems, there are common characteristics. First is low cost. It should be cheap to be competitive. Memory is typically very small compared to a general purpose computer system. Lightweight processors are used in embedded systems.
Yes, stop there. Okay. First characteristic is low cost. You have to make sure the product you are designing is cheap enough. Okay, because many different companies are producing similar product, right? And functions are very similar. So customers have a limited budget. So if you have a price advantage, the customers will purchase your product, right? So you have to make sure you are using a very small amount of memory, right? You don't want to use 1 gigabyte of memory. If 1 megabyte is enough, then why use one gigabyte, right? Just 1 megabyte, right? And CPU, you don't want to use Intel Core i7 inside the TV, inside the microwave, inside the refrigerator. You don't want to use Core i7, right? CPU itself, processor itself is more than $200, right? You have to make sure you are using lightweight, providing just that enough functionality, performance, right? You want to make sure those things. Sang-won, can you please?
And second is low power. It should consume low power, especially in case of portable devices. And low power processors are used in embedded systems.
Okay, stop there. Low power characteristic, and because many embedded systems are battery operated, right? So if you use, for example, an MP3 player, if you use Core i7 processor here inside MP3 player, you have to recharge battery every 10 minutes, right? Then it is useless, right? So you have to make sure it is designed with low power in mind. Okay. Okay, this one. Okay, this one. Kunjong, can you please?
혹시 들리시나요? First, high performance should meet the computing requirements of applications. Users want to watch video on portable devices. Audio should be in sync with video. Gaming gadgets like PlayStation should provide high performance.
Okay.
Second, real-time.
Okay, stop there. Okay, high performance. Third requirement is high performance, right? Again, first one is low cost. Second is low power. Okay, at the same time, you have to make sure, okay, low cost, low power, but your device should provide enough performance. One example is probably your smartphone. With your smartphone, you want to watch movies, right? Some video stream, right? Then your smartphone should be providing, the enough performance to play what? To play at least 30 images per second. Otherwise, human eyes see some interruption in the video, right? Every second, your smartphone should show 30 images, okay, to show your video, right? That is, performance requirement. And Hunjong, can you please, last one?
Second, real-time property. Job should be done within a time limit. Aerospace applications, car control systems, medical gadgets are critical in terms of time constraint. Otherwise, it could lead to catastrophe such as loss of life. And we'll talk more about this.
Okay, real-time property. That is the last property. In some embedded systems requires a real-time property. One example would be what? Brake system in a car. Inside the car, brake system, right? To stop the car, you step on, brake. And what if your brake system say, okay, I'm busy. Okay, I'm going to respond after 100 milliseconds. Okay, you step on brake, then system cannot respond immediately. Then you are dead, right? So brake system should respond to your request, to your event immediately. Otherwise, you are dead. And another example is anti-ballistic missile, right? Ballistic missile. Okay, you are firing, right? And you are firing anti-ballistic missile to hit the moving target, right? Example is, North Korea, for example. North Korea is firing nuclear. What is the spelling? CLNUCL, nuclear, nuclear missile. Okay, North Korea is firing nuclear missile, then the United States firing anti-ballistic missile to hit this guy. It is a moving target, right? So while it is flying, it is changing position, every microsecond. Right, this guy is changing his position every microsecond, and this guy is calculating its position. So there is a hard time limit. In 1 microsecond, within 1 microsecond, you have to compute new position of this guy. If you miss this deadline, then you are dead. Okay, you cannot hit this guy. So the real-time system. Some embedded system, requires that real-time property. So depending on applications, okay? So what do you have to do? This one, okay, we have new faces joined. Kyungchul. Guys, if you have a webcam, please turn on your webcam. I want to see you guys. We can see each other, then I know who is who. Kyungchul, can you please? Okay, Mike, okay. And Sumun, can you please?
It is challenging to satisfy the characteristics. You may not be able to achieve high performance while utilizing cheap components and maintaining low power consumption. So you got to do your best in a given circumstance to be competitive in the market.
Yeah, so think about that. 4 requirement when you design embedded system. Okay, let's go back. Low cost, you want to use a cheap component, right? Lightweight processor, lightweight, very low performance CPU, and power consumption should be low enough. And at the same time, you have to provide high performance. How come, right? You are supposed to use, low performance CPU, but how come you provide high performance? Okay. So it doesn't make sense, right? It doesn't make sense to satisfy those requirements. So there is no solution. So to get competitiveness in the market, you have to do your best in given circumstance. What you have to do is you have to beat other competitor. There are several companies producing similar component. If your product has some advantage compared to other companies, then you win, right? So that's it, right? Okay. So hardware, software stack of embedded system. I told you from a hardware perspective, there is no difference between embedded system and general purpose computer system, right? Hardware, computer system, right? You have 3 components. GP system has CPU, memory, I/O devices, and embedded systems also constructed with these 3 components, right? So from hardware perspective, same, right? Same. And software, probably similar, right? On top of this, on this bare metal environment, someone is porting operating system, whether it is Windows, whether it is Linux or this real-time operating system, someone is porting some operating system on top of that. So we have operating system layer, and many different applications are running on top of this OS, right? OS, that is the one, right? So by looking at this, the hierarchy, not much difference between embedded system and general purpose system. Let's go a little bit in depth with embedded system example. There is one example of embedded system. This one, Jihyun, can you please?
It is mainly composed of processor, 1 or more, memory, I/O devices, including network devices, timers, sensors, etc.
Okay, so from hardware perspective, this example, look at this chip block diagram. You have a very old ARM CPU, ARM 70 DMI. I used this ARM 70 DMI back in 1995, 26 years ago, when I worked for Intel, when I worked for LG Electronics. After master degree, I joined LG Electronics, and I played with ARM 70 DMI at the time. So 26 years ago, very old ARM CPU. And you have memory right here, ROM and RAM. Inside this chip, there is memory, and the other boxes are I/O devices like UART for serial communication with other computer, right? And you have timer. Timer is essential I/O component in any computer system. You should have a timer, right? It is checking. You can check the time, right? Some relative time or absolute time. And here another timer called watchdog timer. We will talk about that. There are normal timer and watchdog timer. Okay. So what is the difference between these two? What do you think? Normal timer, watchdog. What is the function of watchdog timer? 준영. Okay. Okay, Ji-hoon.
I think the watchdog timer is for restoration of the system, maybe.
Restoration of system.
Yeah.
Okay, I think you are correct. Watchdog timer is used to reboot the system, just in case something goes wrong. So watchdog timer is used in applications such as, I have a slide, but some mission to moon, mission to Mars, outer space, where human cannot physically go there, and if something goes wrong, right? If something goes wrong, you cannot go to moon or Mars to fix that problem, right? So the main function of watchdog timer is to reset this whole system. Something goes wrong, only way to restore the system function is a reboot the machine. Okay, so how watchdog timer works? Watchdog timer, in timer, right? Timer, IO device, this IO, you have some counter register, right? So you set, for example, 100, 100. Then clock is coming in, clock like this. Clock is coming in like this, CLK. Then this timer is counting down from this number you just programmed, right? So 100, next number is 99. Hardware is decrementing. Okay, there is a subtractor, adder, right? This hardware adder is doing, subtraction. Okay, from 100, then 100, then 1. Subtraction operation. Okay, so hardware is decrementing this number. Okay, so 98, then eventually it will become 0, right? So it becomes 0, then this timer is generating, this output, the reset. So what you have to do is before this number before this number becomes 0, you have to make sure you refresh this register to 100 again. Okay, before this number becomes 0. Okay, so this time is something like 100 millisecond, for example, right? So within 100 millisecond, if you don't refresh this register to some non-zero number, then reset this reset signal will go up to reboot the whole system. Okay, so within 100 millisecond, you don't refresh this register, then that means something is wrong. You designed. If everything goes fine, then before this number goes to 0, then this register will refresh it to some non-zero value. If everything is fine, but something goes wrong, that will happen. Okay, so watchdog timer is used. Watchdog, right? Think about that dog. Keep watching system. Watchdog, right? Think about the meaning of this word, watchdog. Keep watching the system, right? Something goes wrong, then reset, right? Any question? Is it clear? Okay, let's move on. So from hardware perspective, again, we have CPU, memory, and IO devices. Here you have timer, watchdog timer, serial communication, some GPIO, some general purpose IO, and you have interrupt controller, okay, and so on. Those IO devices. So this chip itself is complete computer system, in a sense that you have CPU, memory, and IO devices. We call that system on a chip, SoC. That is SoC, right? Whole system is integrated in a single chip, SoC. Okay. So another example is iPhone 4, a little bit old, more than 10 years old, right? More than 10 years old, a smartphone. So you have Apple A4 with the ARM CPU inside, right? And flash memory, secondary storage, like hard disk or SSD, right, in computer. And you have some I/O devices like camera, flash, or I/O devices. Right? So a little bit detailed look inside iPhone 4. Look at this one, A4, application processor. Application. Inside here, you have Cortex-A8. So designed by Apple, manufactured by Samsung, right? Samsung is doing foundry business, right? Foundry business, right? Foundry means what? It is just manufacturing the chip, okay? Manufacturing the chip. Design is done by this guy, Apple A4. Chip design is done by Apple. Samsung take the design, manufacture, and deliver the product to Apple, right? So foundry business. Okay, so here you have a CPU, okay, application processor. So inside here, actually, we have, a lot of I/O devices, right? And we have audio codec. So you can think of it as a co-processor, right? Co-processor, helping, okay? Audio encoding, decoding, audio MP3, right? MP3, right? Audio encoding, decoding is kind of heavy, right? Heavy computation, heavy task. So CPU doesn't want to do MP3 encoding or decoding. So that program comes in, then you want to ask audio codec to do audio decoding, right? MP3 decoding to play music, right? Flash, secondary storage like SSD in computer, right? And okay, so those sensors. Okay, let's read this. This one, Guyun, can you please?
iPhone 4 tear down accelerometer detects when the user has rotated the device from portrait to landscape and automatically change the content of the display accordingly. Proximity sensor detects when you lift the iPhone to your ear and immediately turns off the display to save power and prevent inadvertent touches until iPhone is moved away. Ambient light sensor automatically adjusts the display's brightness to the appropriate level for the current ambient light, enhancing the user experience and saving power at the same time.
Okay. Tear down, not tear down, not tear, right? Tear down, tear down report. Okay. So, so smartphone has, sensors, right? Accelerometer, proximity sensor, ambient light sensor. So what is the purpose of having accelerometer? So one example is this, right? Smartphone. So you are changing from this portrait configuration to landscape. Then screen, right? Screen got changed, right? Here, from here to here, screen got changed. So how come? Accelerometer detect the movement, then change the screen configuration. Okay. Proximity sensor here. Proximity sensor. When you take a phone call, the screen doesn't have to be turned on. Right? It doesn't have to be turned on. You are not looking at the phone, right? So like this. So proximity sensor is measuring the distance between your face and phone. So the distance is close enough, then screen will be turned off because the smartphone knows you are taking a phone call, right? To save power. Ambient light sensor. So if you go to a dark place, if you go to dark movie theater, right, very dark place, then screen doesn't have to be bright. So it automatically adjusts the screen brightness. Also to save power, right? To save power. Okay. So there are sensors. Sensors are also I/O devices. I/O devices, right? One kind of I/O devices. iPhone 5. iPhone 5 application processor. One special thing compared to its predecessor is A6 has not only CPU but what? Main memory. 1 GB main memory also integrated in a single chip. So CPU memory integrated in a single chip. All other things are I/O devices, including this flash, right? Including this flash. Flash is also I/O device, right? SSD. SSD in your notebook computer. That is also I/O device. We classify that as I/O device. Hard disk, right? Hard disk is I/O. SSD is I/O device, right? Because why is that? Sometimes that is confusing, right? SSD seems like memory, right? Because it has flash memory inside, right? So, but if I draw computer configuration processor, CPU, right? And you have physical address coming out, okay? Something like 48-bit physical address. Then main memory is attached, DDR, right? DDR4, DIMM, dual inline memory module, DIMM. DIMM is connected to this address. So using this physical address, you are accessing only memory, this DDR, DIMM, right? And hard disk is separate, right? Hard disk or SSD that is separate to access this. You are not using this address. It is not connected, right? So IO, right? So flash, this secondary storage is what we classify that as IO device. Accelerometer, touch screen controller, those are gyroscope, Wi-Fi module, or IO devices, right? S3, Galaxy S3. Okay, so I showed you last time, right? For Samsung has two. Samsung is using two kinds of application processors. One is the first application processor. It is a homegrown Samsung internal, right? Homegrown application processor called Exynos. And the other is the Qualcomm grown, right? Qualcomm grown application processor called Snapdragon. Two application processors, right? Exynos and Snapdragon, right? So the Samsung homegrown Exynos, right? Application processor. So block diagram of Exynos, Cortex, A9, 4 of them. You have cache and main memory, right? Memory or these boxes, these sky blue boxes, IO devices. Okay, so this one, okay, let's move on. Okay, another examples. Let's move on. Okay. System software. Now, hardware is done. So software. So we have system software like operating system and application processor is running on top, right? On top. So system software, operating system, and device driver, right? Operating system and device driver. Okay. So let's move on. Too long to read. Okay. Application processor is running on top, right? Application, all application. Okay, let's talk about real-time system. This one, Jinuk, can you please?
Real-time operating system, multitasking operating system for real-time applications. RTOS is valued for high quickly and or predictably response to a particular event. hard real-time systems are required to complete a critical task within a guaranteed amount of time. Soft real-time systems are less restrictive. Implementing a real-time system requires a careful design of a schedule. System must have the priority-based scheduling. Real-time process must have the highest priority in the horizontal. Next slide. Solve the priority inversion problem. Process dispatch methods must be small.
Okay, let's talk about real-time system, because some embedded systems require that real-time property. Okay, real-time property. Real-time system can be further classified into two: hard real-time, soft real-time. Right? As the name implies, hard real-time, you have to make sure the deadline is met. Otherwise, you are dead. Like brake system in a car, like anti-ballistic missile. Every 1 microsecond, you should be able to compute the new position of the target. Otherwise, you miss, right? You are dead, right? So hard real-time system, soft real-time system, the deadline requirement is not that restrictive. Okay, you better satisfy that requirement. But if you miss, then yeah, that should be okay. But better satisfy the requirement. Soft real-time. Real-time system, when you design real-time system, or when you design real-time operating system, OS, okay? Typically you use priority-based scheduling. Priority-based scheduling, and if you write OS with priority-based, then you would encounter this problem, priority inversion problem, priority inversion. And that can be fixed by priority inheritance. Let's talk a little bit in detail about this problem. What? In real-time operating system with priority-based scheduling, okay, you have this problem, priority inversion, and the solution is priority inheritance. What is that? This one, Hunjong, can you please?
Pathfinder mission on Mars in 1997 used VxWorks and an RTOS kernel from Wind River. Software problems caused the total system reset of the Pathfinder spacecraft in mission. Watchdog timer goes off, informing that something has gone dramatically wrong and initiating the system reset.
Okay, it was very famous story 24 years ago, back in 1997, 24 years ago. There was a mission called Pathfinder. Okay, that mission is to exploring the Mars surface. So NASA, right, in United States, deployed this rover to the Mars surface. Okay, and that is one kind of embedded system, right? Specially designed computer system. And operating system they used here is called VxWorks. That is a name of operating system. The one kind of real-time operating system from this company, Wind River. And then while this rover is moving, while rover is working on Mars surface, system got reset, system got rebooted from time to time. Okay, watchdog timer. So I explained to you watchdog timer, right? Watchdog timer, time, the counter value in watchdog timer becomes 0. Then system got rebooted from time to time. Okay, something was wrong in their system design, and later on they found the problem. The problem was priority inversion problem in operating system. They implemented what? VxWorks. VxWorks implemented priority-based scheduling. Okay, there are many different tasks, many different programs, application programs. Each program has priority. Okay, program number 1. Okay, it has priority number 7. Program number 2, you have priority number 10. Okay, and the other is priority number 3. Okay, so priority-based scheduling. Right? If higher priority task comes in, then what do you have to do? The operating system stops what it has been executing. Then run this higher priority task. Okay, that is priority-based scheduling. Let me explain in detail with what is priority inversion problem is. Okay, Sangwon, can you please?
VxWorks provides preemptive priority scheduling of threads. Tasks on the Pathfinder spacecraft were executed as threads with priorities that were assigned in the usual manner, reflecting the relative urgency of these tasks.
Okay, VxWorks real-time operating system implemented preemptive priority scheduling of the program thread. Okay, preemptive. Preemptive means, again, higher priority task. Here, 3 tasks. Right? Task 1, highest priority. 2, medium priority. 3, lowest priority. So while system is executing this lowest priority task, task 3, what if task 1 comes in, newly comes in? What do you have to do? This is very urgent task. You are executing this, usual task, lowest priority task. Then, urgent task comes in, highest priority. Then system should stop this guy. Right? Stop this guy, preempt, right? Preempt. Okay, you stop. Okay, you stop. I have to run, this urgent task. Stop the task, preemptive, right? Stop it. Then let me follow this story, this timeline. So, system, this robot system, it was executing task 3 with the lowest priority. Then task 3 get semaphore or lock, okay, mutex, semaphore, lock, or mutex to access critical section. So, so we all understand, right? Critical section. What is the critical section? Critical section is some area in memory that is shared by many different many different tasks. Task 1, task 2, task 3, they are sharing this data. Okay, so because this area is shared, critical section. One guy should access this section. Only one guy at certain point in time. One guy is supposed to one of these tasks. Only one guy is supposed to access this task. One guy is done processing data, then another guy comes in. Right? So to guarantee that mutual exclusion, typically we use lock-based, right? Lock-based mechanism. Okay, so lock, 자물쇠, right? Lock. So before you access this data, you have to acquire lock, right? And after you are done with this data, then you have to release lock. Okay, so in the middle you can play with this data. So acquire lock and release lock, right? To access the critical section. So one good example is printer, right? Printer. You have one printer shared by many students, right? Student number 1, student number 2, number 3, and so on, right? So many students are sharing just one printer. Then what do you have to do? Before you send printing job, you have to make sure you acquire lock, right? Then after you use a printer, the next guy you'll use this one. But before this guy use printer, this guy also acquire lock. Then after after the printing job, it is releasing, right? So that is critical section, right? The printer is critical section shared by many different guys. So here, task 3 get semaphore, successfully got semaphore to access critical section. So then here it is accessing this, the shared data. Okay, reading this shared data and updating shared data. Okay, then task 1, urgent task kicks in here because it is urgent task. Okay, so VxWorks, okay, it is urgent task just came in. Okay, you have to stop. You stop. Then I'm going to run this task. Okay. Then here time goes on. Then at this point in time, task 1 try to get the same semaphore to access this critical section. But what should happen then? So this guy, task 3 is not done yet. It's not done with this critical section yet. It is in the middle of using and updating this critical section. So what do you have to do? So you have to, VxWorks, right? VxWorks should stop this guy. Then let task 3 finish its job. Okay, it is something like this. In printer analogy, this guy is printing one document, A4 document. So this guy is in the middle of printing out this document in the middle, right? Halfway done. And this one is more urgent task, highest priority task. So this guy also want to use printer, but this guy is holding this printer, right? So you have to let this guy finish. You have to let this guy finish the remaining job. Then after that you can use, right? So you cannot just, okay, so I'm urgent, okay, so you stop. I'm going to print out, my document like this. You don't want to do that, right? So then in A4 paper, half of the space is the printing, the top half is the document from this guy. The lower half is document from that guy, right? So you are messed up, right? So you cannot do that, right? So here, now, task 1 try to get the semaphore, but because it is holding, task 3 is holding that semaphore, right? VxWorks stop this guy, even though it is urgent, and let task 3 finish its job, right? So the problem is, at this point in time, task 2 came in, but task 2 has nothing to do with this guy. It has nothing. It is not holding. It is not requiring access. It doesn't have to access critical section. It has nothing to do with critical section. So VxWorks, because it is medium priority, higher priority than task 3. So VxWorks says, okay, you stop. Task 3, you stop. I'm going to execute. I need to execute task 2. Okay, so task 2 is continue to be executed to the end. Then task 3 resumes. Okay, and then task 3 finishes each job at this point. Then at this point, now task 1, urgent task, can be executed because now it is released. Lock has been released. Semaphore has been released by task 3. So task 1 can get the semaphore, access this critical section. So if you look at this timeline, how those 3 tasks got executed. So during this time, the priority of task it looks like priority of task got inverted. Is it right expression? Even though the meaning is even though task 2 priority of task 2 is less than task 1, this guy got executed first. Then urgent task next. Right? So priority it looks like priority got inverted. So system is executing lower priority task first here. Then highest priority. So priority got inverted, right? So that is the problem. So how to fix? Priority inheritance. That is Himin, can you please?
A lower priority process could be accessing a critical section, a shared resource that the higher priority process needs. The process with a lower priority inherits the higher priority until they are done with the resource. When they are finished, its priority reverts to its original value.
Okay, let's follow the same example. Okay, but with priority inheritance function. Okay, task 3 got executed. Okay, then at this point, this guy got the semaphore to access critical section. And at this time, urgent task came in. And at this time, this guy want to access the same critical section, but it cannot access. It is not allowed to access critical section because this guy is holding this lock, like semaphore. So what we have to do? VxWorks operating system stops urgent task and let task 3 finish each job. Okay, so if you compare that with previous slide, at this point, task 2 kicks in. Okay, at this point, task 2 kicks in. Okay, I forgot to mention. Let's back up a little bit. Okay, back up. So here, task 1 tried to get semaphore, but because task 3 is holding the lock, VxWorks operating system stops this guy and let this guy finish each job. But before that, operating system is promoting this guy's priority, task 3. This priority to that priority. Okay, priority inheritance. It is inheriting. OS is promoting this guy's priority, lowest priority, to that priority, highest priority. Inherit its priority. So now, look at this. Priority of task 3 is raised to task 1. Now this guy has highest priority. Okay, highest priority. Okay. So now, even though now, so if the time, so the same example, same if you compare previous slide, at this point in time, task 2 came in. Task 2 jumps in. Okay. But the thing is, this guy's priority is less than task 3 now, because task 3 inherited this priority. Task 3 highest priority. Okay. So VxWorks now let this guy finish each job. Okay. then what happens? Task 1 is waiting, right? Task 1 is waiting. So VxWorks, context switch, okay, context switch to execute task 1. Okay, task 1 is now, get semaphore, okay, here, then finish its execution at this point. So now, then task 2 is executed like this. But there is an inevitable time period where priority is still inverted, but you cannot fix. I don't want to say there is a problem by looking at this, right? By looking at this example, right? Printer example. So that this guy, student, printing job, and professor, right? Professor printing job, right? So more urgent, higher priority than student, right? But student is printing its document halfway, A4 document. But even though I has higher priority, right? Urgent job, I cannot. Okay, you go out. I need to print out my document. You cannot do that, right? So there is a period of the time where this I wouldn't say this is a problem, okay, but still, right? Because it is holding. Task 3 is holding that lock. Okay. Okay. Any problem? Any question about this? Okay, let's move on. Okay, so let's read this. Soon, can you please?
RTOS, PSOS, VxWorks, VRTX, UCOS2, PalmOS, SymbianOS, PalmOS,
Okay, skip that part. Yeah.
Android, Open Handset, Aliens project based on modified version of Linux 2.6 kernel, currently supporting ARM, MIPS, and x86.
Yes, thanks. Probably I have to update this PowerPoint. It is a little bit old slide. I don't think Android is supporting MIPS. Okay? In the past, if you Google search, I Google search it and screen capture this one. If you look at this, right? It says Android is supporting here. Android is supporting ARM, MIPS, x86, but I don't think they are supporting MIPS now. Let me Google search. Android wiki. Android. Today. Oh, okay. Now look at this. ARM x86. ARM x86 unofficial RISC-V. Okay, unofficial RISC-V. Okay. So ARM x86 instead of MIPS, RISC-V, right? Okay. So you know what? I just published a book, RISC-V book. Okay, so if you go to yes 24, right? Then check out RISC. This we'll look at this. I just published. Yeah, my name, right? I just published that book. 원리부터 설계까지 컴퓨터 구조 RISC-V 중심으로. Okay. So published date yesterday, right? Yesterday. The book is not is available, right? So you have to wait 3 days, I think, if you want to purchase. Anyway, RISC-V is emerging, right? RISC-V is emerging CPU architecture. So that was designed instruction set, right? RISC-V instruction set was designed by David Patterson, right? UC Berkeley professor. And it is gaining a lot of traction these days, RISC-V. And several companies are designing and manufacturing RISC-V chips. You can purchase, actually. You can purchase RISC-V system these days. So MIPS, this MIPS is almost replaced by RISC-V. Right? Same architect, David Patterson, right? Designed MIPS and RISC-V. If you compare instruction set, they have very similar the instructions and instruction format. And RISC-V instructions are much more, I would say, much more simpler, very simple. So if you are experienced with hardware design, then RISC-V CPU can be designed in one day. Really, one day. Simple, CPU, not pipeline CPU, just simple CPU that can be designed in one day if you are experienced. It is that simple. So the good thing about RISC-V is it is open source, like open source software, open source instructions. So anyone can design and manufacture the chip, no royalty, free of charge. Okay, so side story. So operating system, real-time operating system, the P source, VxWorks, the micro C OS2. I strongly recommend you to check out this book. If you are curious about how operating system works, I think this is a good book you can use. It is explaining with source code, C source code. 20 years ago, before I go to Georgia Tech for PhD study, I look at this book. I read this book. At that time, I didn't know anything about operating system, really, because my major is EE, electrical engineering. But I purchased. I was, before going to United States for PhD, I worked for LG Electronics, where I played with. I told you, right? I played with the ARM7 CPU, ARM7 and SoC, and some people in LG used at that time what OS? I think P source. I think at the time, the neighbor team played with P source, and their job was porting this P source to ARM7, ARM7 SoC. Okay, so I was somehow involved in that work, and I was very curious about this real-time operating system, and found this book in the bookstore, purchased it, and actually read thoroughly this book. Then I felt, even though I haven't took any operating system course before, okay, I was able to understand how OS works, how scheduling, how context switching is done by operating system. So it was very useful to read that book. I strongly recommend you to read this book if you are not understanding operating system, right? So you cannot play with Windows, this heavyweight software like Linux. Linux is also developed by many different people, very complicated, right? But that is done by one guy. This Jim, what is the author's name? Jim Labrose, right? Jim Labrose, right? One guy designed that whole operating system. It is simple actually, and also very useful to understand OS. Okay, so OS, the thing is, real-time operating system, they don't use a virtual memory. So one special thing about real-time operating system, they don't support virtual memory, right? So if you remember computer architecture class, inside the processor, inside the processor, you have CPU core, and cache, instruction cache, data cache, and you have translation look aside buffer, TLB. Right? TLB is taking virtual address as an input and provide physical address, right? So you have main memory, right? Main memory is connected. Main memory connected to here. So why do you need TLB? To support virtual memory, right? To translate virtual address to physical address. The reason why the real-time OS does not support virtual memory is because non-deterministic characteristic. So real-time, right? Real-time operating system should respond, whether it is soft real-time or hard real-time. System should respond around that deadline, right? You have a 1 microsecond deadline, it should respond. But if you have a page fault, for example, page fault with virtual memory in virtual memory system, what is page fault? Okay, the data you are looking for, the page you are looking for, is 4K byte page. This is not present in memory. Okay, that is page fault, right? So that means from hard disk, this 4K byte, from hard disk to main memory, you have to copy that page from hard disk to main memory, and this time is pretty long. It takes something like a millisecond time to copy this guy to here. So that means if the task should be finished in 1 microsecond and page fault happens, then you cannot satisfy the deadline, right? Deadline requirement. So virtual memory is not supported in real-time operating system for that reason. Non-deterministic. Sometimes you can satisfy 1 microsecond requirement. Sometimes you cannot because page fault. Okay, so that is why RTOS does not support virtual memory. And that is why I think reading this book is easy, because it does not support virtual memory, right? Okay, and the last slide for today. UC Linux. UC Linux is, where is it say? Where does it say? UC Linux. Where is that? MMU list. Next page. MMU list. Memory management. Does it say? Limited resource, cell phone set-top boxes. Okay. So embedded Linux. Embedded Linux has UC Linux. MMU list. Did I say something? Micro C Linux? Okay, sir. Micro C Linux. Without memory management unit. Variation of Linux kernel previously maintained by folks target microcontrollers without memory management unit. So memory, we typically say the TLB is located within MMU, memory management unit. Okay, so that means UC Linux does not provide virtual memory support. Okay, that means you can that can be used in system with a real-time constraint. Okay, it's a Linux-like, but somewhat providing that capability, real-time, the property capability. Okay, that is it for today. Let's just stop here, then continue next time. Any question? Okay, see you next time. Bye.